All right, so when we take a peek at parallel lines, normally those are labeled with lowercase letters, or you may see some markings on a line somewhere. So in this case, we've got lines A and B here are cut by what's called a transversal. Transversal is just a fancy word for saying, here's a line that's going to go through both of my parallel lines and make all these angle measures for me. So basically what we're going to do is we're going to use our two parallel lines up here, and we're going to take a peek to see what these angles are and what kind of relationship that they have. Are they equal? Do they add up to 90? Do they add up to 180? Because that's going to kind of help me with some of the math. So for instance here, our vertical angles are congruent. Examples 2 and 3. Now here, 2 and 3, what you'll notice is they share what's called a vertex. They share a common point, but they're across from each other. Okay. Where would be a couple other places that you see vertical angles on here, just using the numbers? So if 2 and 3 share that common point, are right across from each other. 1 and 4, I was going to say there's several other pairs. 1 and 4, where else? Yep. 6 and 7, and where's the last one? 5 and 8. Okay. And those are always going to be equal to each other. So like if I knew, for instance, that angle 1 was 60 degrees, then angle 4 has to be 60. And that can help me when I'm trying to figure out missing angles. Okay. Corresponding angles are also congruent. Congruent, again, is just our fancy mathematical way of saying equal, or having equal size. Now you start to look at this. Now these get a little more interesting. You're like 1 and 5. Now how am I going to remember this type of stuff? Now again, sometimes I think a little strange, but sometimes getting a picture in your mind works. I start looking at something like this and I see a sandwich with a toothpick going through it. So if I start to look at it that way a little bit, I go, okay, so 1 and 5. Well, what do I notice? I notice they're on the same side of the toothpick, but I notice one of my angles is outside the sandwich, because again, kind of, here's my burger going through there. And I've got one on the inside. So again, where are some other places, same side of the toothpick, you've got one angle in and one angle out? So we got lots of these again. Where's a one in, one out pair? There's 3 of them. Okay, 2 and 6, so we just head to the other side. I'm with you. Yep, and just because the one that's outside's down below doesn't make any difference. It's just same side, 1 in, 1 out. And then the last one's just kind of process of elimination here, 4 and 8. Okay. So 1 inside, 1 outside. And you just sort of start looking for these little patterns. Alternate interior angles, this one is the one that's going to show up most often on any type of testing. It's the Z shape. Now sometimes that Z may not be this way, it may be up and down and look more like an N. But if you kind of look, you're like, oh yeah, it kind of zigs and zags here. There's one on each side of my transversal, of my toothpick, but they're both inside. So I don't have a lot of these. I actually only have one other pair. If you run Z through there, where's your other pair going to be? Okay, and it's those angles that are getting trapped inside are the ones that are my alternate interior angles. Okay, so 4 and 5. Because they're inside. They're squished into my sandwich, or in between my 2 parallel lines. Now, alternate exterior also use that Z shape, but notice exterior. They're on the outside of my parallel lines. So you notice here with 1 and 8, where I had kind of my little orange shading in here before, 1 and 8 are the 2 angles on the outside of that. I had 3 and 6 as my alternate interior, and now I have 1 and 8 outside. So if I do the same thing with my other pair, 4 and 5, we check out the angles that are just outside of that, which would end up being 2 and 7. And again, just having this little picture up here will be handy when you're trying to do some of these playing around with some of our problems for the homework. A lot of clues come from just the words. Same side, so on the same side of my transversal. Interior. Well, that makes sense. These are on the same side, and they're both inside, 3 and 5. So I look on the other side, and I see the other two that are there. So in this case, it'd be 4 and 6. They're on the same side. They're on the interior. They're between my parallel lines. And then again, real straightforward, same side, exterior, or the outside. 1 and 7 are on the outside. Move to the other side here, 2 and 8 are on the outside. So a lot of times just understanding some basic things. But again, also notice my first 4 here, so my alternate angles, my corresponding and vertical are all equal in size. But then when I get to the interior and exterior, they're supplementary, which means they add up to 180. They're not necessarily the same. So that's one little adjustment you've got to be ready to make, because if I set them equal every time, that's not necessarily going to get me where I want to go. So let's actually do some problems with these. So in our trapezoid here, AB is parallel to DC. Okay, that's good to know. What's the measure of C? Now you may not see this right away. So sometimes I have to look at this and I go, okay, these lines are parallel. I'm going to kind of extend this a little bit. And I'm going to start looking at it sort of like that picture is up above, because the picture up above is something that I know. Okay, so these lines that I'm drawing through are like a transversal. So for instance here, BC would be a transversal. It's like my toothpick going through my sandwich. So if I look at these two angles, they match with one of my angle types from above. Well, let's see what I notice. They're inside, so that would get me to something that's interior, and they're on the same side of my toothpick. So same side interior. So what's that mean? Well, they're supplementary, or they add up to 180. So these two, 80 plus something, I don't know what this is, adds up to 180. And then I just got to subtract the 80 over to get my x alone. And I find out what that value is going to be. Okay? But in order to get that, of course, I have to know that it's same side interior, because if I make it congruent, then I'd say it's 80, and that wouldn't be right. Okay, so having a basic knowledge of these, or at least what types they are, helps out.
So are most of the problems going to like that to make the final?
It'll be, a lot of it's going to be missing angle type things. Yep, absolutely. So let's see here. Move up a little. Example 2. In the figure below, B is on DE and DE is parallel to AC. Which of the following angle congruences must hold? Now once again, I'm going to go ahead and I'm just going to sort of extend these out a little bit so I know that they're going through, because they told me these two lines are parallel to each other. So now, I'd mentioned before, more times than not, when you get into a situation like this, alternate interior angles are going to be the things that seem to occur. So that Z shape might be something I want to keep an eye out for. So if I look at 1 and 2, well, they're right next to each other. So that doesn't really go with anything we've been doing. Thank you. So when I get to 1 and 4, I'm like, okay, well, let's see. 1 and 4. No. It's over there. And probably not. 2 and 3, well, that's sort of like 1 and 2 where they're just sitting there next to each other. Now 2 and 4, Now 2 and 4 has some possibilities here, but wait a minute. 2 and 4, they're on the same side, and they're interior. So that'd be same side interior. Yeah, but they're supplementary. Okay, they're not equal to each other. They're not congruent. What about 3 and 4? 3 and 4. Oh, there's that Z shape, which means those are alternate interior, and alternate interior, those are congruent, okay? Now, a lot of times, can I visually look at these and maybe tell if a couple are the same? Maybe, but 2 and 4 even look kind of the same, so I don't know if I'd generally go with that idea unless it was really obvious. But alternate interior, I'm telling you, that zigzag, that Z, it happens a lot on these. So something to watch out for. All right, let's see what else we got here. Example 3. In the figure below, ABCD is a trapezoid. E lies on AD and the angle measures are as marked. What's the measure of BDC? So this angle right here. Well, let's see. Now, am I going to be able to get it directly? Maybe, maybe not. There's a couple of things I know for sure, though, that might help me out here. When you ever have a straight line, how many degrees is that? Okay, so a straight angle is always going to be 180 degrees. So these all add up to 180. Well, I know this is 105, so I know these two would add up to 75, but I'm not sure how to find this. So let's see. I know these are parallel. Let's see if I can do that Z thing. Let's see if that helps me at all. Because I'm telling you, it shows up a lot. Ooh, not the exact angle I want, but this angle gets trapped in there too. So if this is 30, alternate interior tells me this is going to be 30 as well. And now I can figure it out because I know this part, and I know this part, and the only part that's missing is what's here. So if I take my 180 and subtract the 105, and also subtract the 30 that I just figured out from my alternate interior angles, I find out my missing measure is 45 degrees. So there's lots of ways you can go after these, but you'll notice a lot of times you're going to get either one of those alternate interior or something like that just to give you that one little piece that you need. And that's kind of like just solving a puzzle. All right, let's see what else we got. Because they're not usually real straightforward, just like that front chart, and here it is. It's usually not going to be quite that easy. We got to build a little. So let's see. The figure below, M and N are parallel. All right. Transversals R and S are marked to form an angle of measure X, and two other angle measures are as marked. What's the value of X? Now here would be the nice thing. If I could figure this angle out, then this would be nice because these two are vertical angles, and I know vertical angles are congruent. So let's take a peek here for a minute, see if I can find something that would help me. So I start to look, and I'm like, let's try to do something that I know. So I take a peek at this, and I go, okay, here's a triangle. Now, how many degrees are there in a triangle? Okay, 180 degrees in a triangle. I know this angle. Can somebody tell me what this angle is and how I could figure it out? Right, it makes a straight angle, and I know what part of it is. So this part would be 180 minus 100, or 80 degrees. So I know that part. Well, if I know a triangle is 180, and I know those two angles, this angle would be 180 minus the 65 minus the 80, which would make this 35 degrees. And we looked at the start and said these are vertical, so if this is 35, this also has to be. So it wasn't straightforward. It wasn't just one thing I could calculate and figure it out. I had to do a little bit of extra work, but remembering, a triangle is something I know. And there's other ways you could do it. It'd just take a little bit longer. But that's going to keep life really simple on us. And as we kind of keep bopping along here, all right, in the figure below, B is on AC, all right. E is on DF, okay. AC is parallel to DF, so these are transversals. BE is congruent to BF. What's the measure of DEB? All right, now let's see here again. Is our old buddy alternate interior going to help us? There's my Z, so it traps this guy in. So that'd be 35 degrees. Now, let's see how much geometry we remember. If you have two sides of a triangle that are congruent, what's that called? It starts with I. Isosceles, okay? So I have an isosceles triangle because I have two sides that are the same. The two sides that are the same, their base angles have to be the same. Ooh, I got to remember geometry with this. Oh, yeah. Which tells me this is also going to be 35. Now, I'm looking for this angle out here. So you're like, oh, it comes back to the straight angle again. Because if I know that this is 180, and I know this part's 35, I've just got to subtract it. And get my angle, and I'm good. Now, if it was multiple choice, they're always going to say that drawings aren't made to scale, and occasionally that's true, but a lot of times they are. So here you might even notice that that's obtuse, that it's going to be greater than 90, so I wouldn't pick anything that was less than 90. Again, just making sure. And 6, unfortunately, we are going to have to skip because I ended up putting the wrong choices in. And I was looking at it this morning, and I'm like, crap, that was bad. So we're going to go past number 6 for right now. Hopefully I can get that fixed here, and we can go back and hit that up tomorrow. All right, so 7. Don't let all the fancy language get you. We're going to get to the end here with what we're trying to see what we're finding here. In the figure below, transversal R crosses both P and Q, and A and B are measures of the angles between 0 and 180. Lines P and Q will cross somewhere to the left of transversal R. So what they're saying is, this line will keep coming the way it's going, and this one's got a little bit of a slant and is starting to come up, and somewhere down here to the left they're going to cross each other. So, which of the following statements best expresses a true relationship between A and B? Now, here's where we got to think a little bit. Let's just say these two lines would have been parallel to each other, and these two aren't. If they were, these two angles on the inside would have to equal 180 degrees because they'd be same side interior. But if I look at this and I say, okay, these are coming together, that means as I continue out to the right, these two lines are going to get further and further apart. Okay, well, what does that mean? Well, basically what that means is, if this would have been 180 going straight and it's getting bigger, it means this has to be greater than 180 degrees. So if these two together are greater than 180 degrees, that would end up being K. It wouldn't be less, they'd have to be on this side because it's getting smaller and kind of squishy on this side. For them to be equal, they'd have to be parallel. We know they're not equal, they're same side interior. We know they're going to add up to 180, but we know in this case they could be greater than that. So lots of things to take into consideration with that. And finally, quadrilaterals, we're going to keep life kind of simple here. The sum of the interior angles of any quadrilateral, 4 sides, is 360. And we'll talk about some of the other shapes and figures tomorrow. So to find the measure of angle C, it's a quadrilateral, 4 sides. I'm going to take 360, and I just would subtract the other angles that are there. So let's see. Somebody, when they figure it out, let me in what? 116. Now here's an example of not drawn to scale, because you look at that and you're like, man, that doesn't look like it's a lot wider than, this one looks wider than that one. So that's the time that you've got to not let that fool you. It just kind of gives you a general guide, but not an exact one. And then to understand the shapes and how they work, because again, it's going to come into play. When you have a rectangle, several things to keep in mind. This is going to look like artwork when we're done. Rectangles have 4 right angles in the corners. So we know that. When it says the diagonals are bisectors, that means that these two pieces are the same size, and so are these two. And we also know that opposite sides of a rectangle are equal in size. Okay, so lots of little things. But the big one that will show up in the ACT a lot is that they're bisectors and end up being equal or cut in half. Okay. Squares and rhombus, very similar in what they have, except for one big thing here, and that's the right angles. Square has them, rhombus doesn't have to. They can be, but they don't have to. A square, we also know, all the sides are equal. That's also true with a rhombus. So if I know what one side of a rhombus is, I know what all the sides are. It also mentions that their diagonals are perpendicular bisectors. Now here's what that means. Not only does it cut the diagonals in half, but it also creates right angles right in the middle of my shape. So you'll notice the only difference so far between these is this has to be a right angle and this doesn't. The only other thing I know with a rhombus is that my opposite corners are going to have equal angle measures. But again, a rhombus can have right angles, but it doesn't necessarily have to. Squares do. That's your big difference with those. And kind of having the picture to see that'll help, especially when you're working on the first practice problems here. And then kites are pretty basic. Their diagonals make right angles. And then your legs of your kite are going to be equal to each other. Those are the basics on these to kind of keep you in the loop with these to be aware of. So how can we use this now to actually do some math? Are they going to actually start making drawings on the ACT? No. But understanding that will help us with the math on this last part. You have almost survived. All right, rectangle ABCD with diagonals AC and BD intersecting point E shown below. Rectangle ABCD is a square if and only if triangle ABE is congruent to which other triangle? Now this actually seems like it'd be a tricky question, but it's not. To be a square, all the sides have to be equal, which would mean this would have to be equal to this and this and this. Well, we already know in a rectangle, this side will be equal to it. So when I start to look at these other triangles, well, ACD, that doesn't really even make sense. That's like half the triangle. Those aren't the same size. That's like a quarter. That's like a half. Well, that's too big. Not the same size. ADE. Now I start to look at that one. And visually at this first, I'm like, well, they're not equal in size. True, but if they were, that would mean this side would have to equal that side. That's looking pretty good. Because if these sides equal, then these sides also have to equal, and then it's a square. But let's just check. BAE, well, that's the same triangle. That's kind of silly. So it's not that one. BDC, again, is too large. It takes up half of my rectangle. And CDE, well, we already assumed that with a rectangle, those are going to be the same. So we already know those are. That wouldn't help us with our argument. And that's going to be the one that's going to be tempting to a lot of you. You're going to be like, yeah, they look the same. That's it. But for it to be a square, one of the sides opposite that would have to be equal. So lots of in-depth thinking. And to put some of you at ease that are sitting here in a panic right now going, oh my gosh, if there's a bunch of questions on the ACT like this, I'm done. This is a type question, because I mentioned before how it goes from easiest to hardest. This is the type question that's going to be somewhere up in the 40s. So when we talked about strategy before and focusing on the first 30, 35 questions, and then just kind of doing some of the others if we have time, this would be one of those questions in that category. Because remember, on the ACT, I'm not expecting most of you are going to know what to do on every single question and be able to just breeze through. We want you to do the ones you're comfortable with. So this would be one of those I'm probably going to end up picking my favorite column on. But if not, it's always good to have that little bit of knowledge in the back of your mind. 10. In the rhombus shown below, diagonal AC is 8 inches long and BD is 6. Now we remember from over on the other side that they're bisectors of each other. So if BD is 6, that makes each of these pieces 3. And if this is 8, that makes each of these pieces 4. And it also mentioned that they were perpendicular bisectors. And here's where that comes into play. What's the perimeter of the rhombus? Well, I know all the sides are equal in length, so if I can find out how long one side is, I know how long all the sides are. So let's take a little deeper look here. Right triangle. I need the hypotenuse. Wow, Pythagorean Theorem for like the third straight unit. A squared, so legs squared plus legs squared is going to be my hypotenuse squared. So 9 and 16. It is. Now again, be cautious. You're being asked for the perimeter. Like this happened to some of you on the last quiz. You did a great job of figuring out how long one side was, but it asked for the perimeter. So if that's 5, this is 5, this is 5, this is 5, my perimeter is going to be 20. So don't just think x equals is your be-all, end-all. Because in this case, it's not. And finally. The figure below, ABCD is a rectangle. Okay. If AC is 13 inches long and BC is 5, what's the area of the rectangle? Okay, first question. How do I find the area of a rectangle? Okay, base times height, length times width, however you want to call it. So I have this. I need this. Well, let's see here. Oh, yeah. Rectangles have 4 right angles. Never guess we're going to have to use again. Okay, we've got the Pythagorean Theorem, but this time I have the hypotenuse. Right. Hypotenuse squared minus side squared. Now, if some of you still want to do 5 squared plus x squared equals 13 squared, that's fine. And this actually comes out nice, but again, don't just go with the 12 and say, woo, I'm done. No, area. Base times height or length times width. Okay, so make sure that you finish it. So your job is to work through as much as you can do with practice A. Answers will be up when you walk in tomorrow. We're going to do a little bit with some other shapes besides quadrilaterals, but it'll be real short. And then we'll take some questions on these. We'll work on practice B and kind of get a feel for that before we start moving into the quiz preview and then the quiz up on Friday.